So let's start real basic here. Okay, so say it again. You said momentum and impulse.
It's
And that.
momentum, collisions, and impulse.
Okay, yeah, we should go over that, what we did before with the impulse. Okay, so let's just do an impulse one real quick. Okay, car at stoplight. And okay, so go ahead and read this, and let's see if we, do you know how to find the force? That's what we're going to do here. Find the force on the man. So I'll go through it, but if you could tell me which equation you think would be the one to use.
Okay, so the equation to use would be I always forget what this one stands for, but it's delta P equals force times time.
Yeah, exactly. That's called impulse.
Okay, impulse.
Yeah, remember, both of this is an equation, so the left-hand side is impulse, but so is the right-hand side. They're both impulse. So change in momentum, and you know momentum very well, it seems by now. Maybe it's a little trouble using it in a problem, but you know P equals mv. You need a mass and velocity.
Mm-hmm.
And so, I mean, I like to do, and it looks like you're doing that too, which is good. You solve for what you need. So that's exactly right. There's the equation. So, well, F must be a change in momentum divided by time, of course, right?
Mm-hmm.
So if we want that, well, what is the change in momentum? Remember that delta symbol, it means a difference, a change. So some final minus some initial. You always subtract the final minus the initial. What do you think the next step is? Give you a hint.
Okay.
What would this new equation be if I substitute, right? I want to put that into there. So I just want to solve, or I just want to put it in for PF, momentum. So, but I know that momentum is mass times velocity. So it's some mass times a final velocity minus the mass initial velocity. Good enough?
Mm-hmm.
Sure.
Yeah, that makes sense.
So, well, now we have all these values. If you don't think so, take a minute and then I'll convince you. But we have, how many values we have? We have 4, right? Here's 1, here's 2, that's the same. So whatever, 2, 3, 4. And we have that in the problem. We got M, 80 kg for the guy, T 0.3, V final 40, and VI would be what?
So that's the initial
Yes.
0.
Yeah, he's just sitting there. He's scrolling Instagram on his phone. He's not moving. So plug in the numbers, right? And you can say, oh, that's 0. So you should get a very large force. He's getting hit by a car here. So 80 times 40, which is like a huge acceleration divided by 0.3. You know, he's getting, he's dead. So kilonewtons or 10,000. I don't remember what you guys do. Usually have it in SI, but there's that's the 1,000. Remember, K is thousands. Huge force. And I think it was actually pretty similar to the one we covered. And that's kind of like the basic impulse problem. Probably the most, probably actually pretty similar to something you might see. So good enough? How's that? Any questions?
So when you were plugging in the equation, did you use, so like for MVF, did you use like 80 times 40?
Yes.
Okay.
That's what I did in the calculator.
Okay, that makes sense.
Yeah, the key here is, as always, your relationship or your equation that you need that governs this whole thing. But then also these other guys that come in, right? Because they're probably not going to give you the momentum. They're not going to give you the change in momentum divided by time. It's too easy, right? Remember these two things, that it's a change. And then, of course, the relationship between momentum and velocity. And you'll be good. We'll do some more for sure, but okay. Okay, so I got 2 parts here. Yes. They want final momentum and average force. Which equations should I use?
Okay, so for the momentum, you should use P equals M times V, and the impulse equation, delta P equals force times time.
So yeah, that's exactly right. And both of these are fairly straightforward. Let's do the easy one first, because we have both these things. I mean, oh, sorry, we don't have. Oh yeah, that makes sense. Okay, we don't have the mass. Okay, so we got to solve for the average force first. So delta P equals F over T, or F equals delta P, which is actually, I'm just going to skip that. Actually, I won't skip it. There's that. I just solved for F, of course. But what is delta P? Well, it's a change in momentum. And what is each of these? Well, this is always true forever and ever, ever, ever. So mvf, the final velocity, minus mvi, initial velocity, divided by time. Oh, sorry. That's I did. I messed it up. I done messed it up. We do have the mass, obviously. Usually you will. Hits ball mass, sorry, 51 kg. So you could do that because you have the mass, but it doesn't matter. We're in this now. So It's basically the same thing as before because it's just sitting on the T. It's not moving. Got a stoplight. The thing's not moving, right? So
Yeah.
average force, use that impulse equation, and you would get, well, remember this 80 meters per second, that's your final velocity because he swings and then he hits it. And so just before he hits it, it's not moving. The initial velocity is 0.
Mhm.
So 51, God, not kg, it's a golf ball. So fine, 51 grams. So 0.051, right?
Mhm.
Write that down if you want, actually. 0.051 times, and then it's moving 80 meters per second divided by the time. Great. Again, this is a large force. I mean, golf ball. 680 newtons. I like to be a little more clean, but just let me know. I can rearrange that if you want me to.
Okay, and this one was for the average force.
Yes, Newton's
Okay.
force. Impulse equation. It's all about that. And then this is the step you're going to have to do on your test. Figure out if it's impulse or not. Remember the equation, and then go through this process here. Delta P is this. Oh
Mhm.
yeah, I got to plug each one of those into there. So this is what you're going to have to do. Okay.
Okay.
And then the final momentum, well, we basically kind of calculated that, but we got it, just can easily do that. Okay, that's 2 impulse. We can do some more later if you want. When's your test? Tomorrow or Friday?
Tomorrow.
Okay. All right, then we're gonna move. Okay. So you're definitely gonna see an elastic and an inelastic collision, both of these. And just remember what's conserved in an elastic collision, I'm asking.
What is conserved?
Yeah, in an elastic collision.
Well, in an inelastic equation, the kinetic energy is not conserved.
In an inelastic, yeah, good. Is momentum conserved?
Yes.
Yeah, it should always be conserved. What about an elastic collision?
In elastic collision, momentum is always conserved, and kinetic energy is also conserved.
Yes. Yes. So momentum always conserved in both types of collision, and kinetic energy only in elastic. But then, and so remember, elastic billiard balls, they're not in contact anymore after the collision. That's elastic. Kinetic energy conserved.
Wait, okay. So in elastic, kinetic energy is not conserved and momentum is conserved.
Did you say for elastic?
Inelastic.
Yes,
Kinetic
inelastic.
energy is not conserved. Okay.
Yes, yes,
And for elastic, momentum and kinetic energy are conserved.
yes.
Okay.
And I'm writing it down for you just to keep it as short as possible. This is what you want to think about. Billiard balls, no contact, KE conserved. Let's do you one better here. KE conserved. And there's an equation. It's Ki equals Kf. Yeah. Momentum also conserved. Momentum is always, always, always conserved.
Okay.
And then inelastic. Think like the one you looked at was the train. Remember that the train car and they got attached, or Velcro, like they stick after collision. Stick after collision. And that's pretty clear. I mean, billiard balls, they obviously don't stick. And then you would say Ke not. And then momentum, just always consider it conserved. Right. So just real quick, not equal. That's what that means in math, right? Yeah, that's your like cheat sheet or study thing or whatever, like to remember elastic, inelastic, because you're going to see both of those. We can, yeah. Okay, and so this. Okay. Okay, so you're going to go through this. You're going to write down what you have, right? In fact, let's go through that as we do, because I haven't been doing that, but it is still always the most important step here. Got that. Okay, hooray for us. And it's moving too. We got a V1, right?
Yes.
It has a collision. It's not, he should tell you if it's an elastic collision, but as soon as you see this, you say to yourself, or you write it down on your paper, you say elastic, oh, kinetic. You can write that down right next to it, which means kinetic energy is conserved. You got another mass. Of course, you're always going to have two objects. And look, it's at rest. So that means V2, 0. Find the speeds. So I'm going to use this notation. Just let me know if he does something else and we can work with it. The prime means after the collision, final, right? So if we want to find these speeds, what should we do?
To find the speeds.
Actually, let me say this before you answer that. The way you think about this, and you're going to think about, you should think about this tomorrow, is basically, it's going to be momentum. Obviously, you know that. But then that's the question you want to ask yourself. Is it elastic or inelastic? And you say, the answer to my question, which equation you're going to use, well, momentum's always conserved. That's the equation. Momentum's always conserved. That's the equation. Use this one if you have to, right? So now go ahead. How do I find the speeds of both these guys?
To find the speed, we would use
what is momentum equal to?
momentum equals mass times velocity.
Yeah. So that hopefully that puts you on the right track there.
So P equals M times V.
That is true, and that's always true. That's not, I mean, is that going to help us here? I mean, I guess the way I asked that, no, but conservation of momentum. I really want you to try to see that. This is the equation. And maybe since you're thinking about speed, you're not thinking about momentum, but if you're thinking, you need to change that. And if you need to start saying in your mind, if I'm thinking about speed, I'm thinking about momentum.
Mhm.
Why? Because I mean, this same equation is literally just m vi equals m vf, right?
Mhm.
But remember, we have two objects here, so we have to consider them both. And so it's not right that, but we still use this equation. But then we say, okay, what is the initial momentum? That's the initial momentum. We know it's okay, pf, fine, but it's also equal to the sum of all these momentums.
Mhm.
So what would I put right here?
Wait, right where?
Right, for this equation for initial momentum, like what is p1 equal to?
Um, I don't know. I'm still confused.
So if momentum is m times v, then the momentum of the first object is just m1 v1.
Oh, okay.
So what is p2 equal to?
M2 V2.
Yes, but you got to make sure you're able to look back and see what we're doing here and why. It's because, well, that's always true, and that's what we start with. Okay,
Mhm.
what is the left-hand side of the equation? It's that.
Yes.
Why? Because of this. So, I mean, if again, what I just say, this is what you start, conservation of momentum. What's the left-hand side of that equation? What's this? Yeah.
Yes.
So then if I did the left-hand side of the equation, that's what this whole thing is here. Conservation of momentum. What is PI? Well, you just sum up all the momenta, because we have two objects. It's the system, right? It's this system that we have to do the initial momentum. But I also know that, oh yeah, that's true. So then P1 is just my subscripts.
Mhm.
Okay. Then the left-hand side of the equation. I'm sorry, the right-hand side of the equation. Right? What's this one then? Well, it's still this, but it's a little different now because it's after the collision. So it's a final velocity. M1 V1 primed to denote final. Sometimes you might see I and then another subscript I, but we're not using that. But it's just the momentum added together. The individual momentas added together.
Wait, what is the V1 primed? What is that?
Final velocity
Oh,
of the first object.
okay.
Because we have a collision, right? So there has to be an initial velocity and a final velocity for both objects. That's why we just can't write VI, VF, because I don't know which VI that's referring to. Is it referring to the first object or the second object?
Okay.
So again, go through it. This is true. You got to start with conservation of momentum. And then I said, oh, okay, what's the left-hand side, right?
Mhm.
For those reasons that we just went through. And then, oh, okay, I just did that. Cool. Right for me. Now what's the right-hand side? Oh, it's PF. Well, what is PF? Well, it's this, what we just did, right? And so the final thing you get is this. This is the initial momentum of the system, PI. And guess what? It's equal to the final momentum because of conservation of momentum.
Mhm.
So then M1 V1 prime, that final velocity of the first object times its mass. And then the second momentum. Well, at P equals mv. Conservational momentum. You want to divvy up the left-hand and right-hand sides. So remember, this first object was just sitting there. Or this, I'm sorry, the second object was just sitting there, right? So that's 0. No momentum in that second object initially. And I'm going to change what I said a little before. Just that it is too complicated for what you're going to see. Find speed of second body. If first object. So I'm going to say that we give in the first object here. Otherwise, you got to use the second equation, and it's not useful to you because it's too much for what you're going to see. And so, but it doesn't change anything we talked about so far. So now I just need to plug in the numbers. But again, this process of getting from here, which is just your standard conservation of momentum, all the way to here, that's the key here.
Okay.
So we'll do another one for sure, but I want to solve for V2 primed. They're asking me I want the speed of the second body after the collision.
Okay.
It's just keeping track of your variables again. I want the final velocity. I don't care what you call it. I called it with a prime, the final. And so I need to solve for it here. So then I would say, M1 V1 minus M1 V1 primed, initial velocity of the first object, final of the first object equals M2 V2 primed. Divide by both sides by M2. And then you can do this. The initial was 3, so 1. 1 is 4. Okay, so 2/3. We're going to do the exact same thing because it's what you're going to see. If you have any questions or anything?
No, it's starting to make a little more sense.
Okay, good. I hope that then this next one, I'm just going to do the exact same thing and maybe have you kind of guide me or, do it and I'll guide you. Yeah, I know you're late and I will try to make up for this as much as possible. Make up for that. Okay, so. Okay, so I'm just going to do the same thing. Whoa. Okay, ball of mash 1.5 kilograms hits the ball. Another one. Woman, 3. Find speed of second ball. Okay, so I'm gonna start this for you because you need to do this every single time. M1, got two objects. Oh yeah, cool. M2. Now you tell me the initial velocities of these things.
So M1 is 1.5, M2 is okay. So the velocity. Okay. So the initial. Okay, so the initial velocity of the first ball is 2 meters per second.
I agree. What should I write down right
Um,
now? You're 100% right. How do you write it down?
you should write that VI.
V1.
V1 equals 2 meters per second.
Now, if I want to try to follow that notation there, if you said VI, okay, you know what? Let's do that. Let's write down VI rather than just show you down me. Let's write down VI. Okay, what do I write down for the velocity of the second ball?
V2.
Yeah, we could do that, and it's 0 meters per second, right?
Mhm.
But it's a little weird. I mean, I've always said this to you, and it'll always be true, is that as long as you know what's going on, it doesn't really matter. I don't care what you do. But you might forget that this is, oh, the initial velocity of ball one.
Yeah.
And you might even forget that that's an initial velocity if you don't have some sort of subscript. So that's what I was saying before about if you do use 1 and 2 without the primes, you might say 2I. It's just a little cumbersome. It's a little harder to write. That's why I like the V2 primed for the
Okay.
vinyl.
Okay.
So initial, these are initials. What else should I write down?
Okay. So you have your masses and your initial velocities. So you have the final velocity for ball one, which is 1.5 meters per second. So
What do I call that?
VF prime. I don't know.
So it's redundant for the prime because I'm using that primed.
Okay.
But if you said V1, because you're right, what the words you said are 100% right. Perfect. The velocity of the ball after a ball one is, but you just need a good way to denote it and write it
Okay.
down for math. So like I said, you could say V1F, and then you'd have to say V1I here.
Okay.
But if you like that, that's what you should do. I like the prime. That's why I use the prime for the final.
Okay. I think I just don't really understand what the prime is.
Mm-hmm. So let's not use it then. Let's stop using that and say V1F.
Okay.
That might be a little better for you. And so V1I and then V2I. Yeah.
Okay. Yeah, that makes more sense.
Okay, good. So then what else? I need to find something. What do I need to find?
You need to find V2F.
Yes, exactly.
Okay.
Great.
So,
How do I do it?
equation that you want to use is the Okay, so you want to, okay, so the equation you want to use is P equals M times V, and then you also have the PI equals PF, and then MBI equals MBF.
So that this is true in general, but for one object, we've got more than one object. So you're so close. This is all, this doesn't really help us though, because it's not, remember, it's the initial momentum of the system, which is both of the objects. So what do I write down instead? Notice I'm not necessarily saying you're wrong. It's just for this problem, this isn't really enough for us. We can't, it doesn't give us enough information because this is only for one object, right?
Mhm.
So how do I write that down for two objects?
Oh, okay. So, okay. Is it like the PF equals M1 V1 plus M2 V2?
Yes, yes, yes.
Okay.
So tell me what to write down.
So you're going to initially write down PF equals M1.
Let's do the left-hand side. Let's do
Oh,
PI first.
okay. Okay, so instead, okay, so you're going to do PI equals,
Here, I'll help you. Yeah,
M1 V1 plus M2 V2.
V2I, the initials, the initial speeds.
Oh, okay, that makes
Be-
sense. Okay.
Because we're dealing with the initial momentum. Okay, so what's the equation for PF then?
Um, is it the equation that I already said, M1 V1 plus M2 V2?
Not exactly, yes, but not exactly. So
Oh.
keep that in mind. This is what you said, and this is what it is though, V1F.
Oh, okay. So I'm just leaving now.
Yes, you're I was gonna say on it, you're like 80% right, but it's final. We got to deal with that final momentum. So we got to add that final velocity. Yeah.
Okay.
So what do I do now?
Okay, so we're trying to find the speed of the second ball. So you're trying to find. So wouldn't you have to find just the final velocity since you have both initials?
Yeah, you've got both initials and the final of the first one too.
So all I would have to do is find the final velocity of the second one.
Yes.
Okay,
Yes.
so
So how do I do that?
you would use the PF equation that we just used, but you have to.
This one.
Okay, so you use PF equals M1 V1 F plus M2 V2 F. You'd use that one.
Sure. Yeah.
And then,
So what?
okay,
Tell me what to write down, I guess, is what I'm asking.
okay, so we're trying to find V2F, so you have to isolate that, right?
But which equation do I use? I use this equation.
Wouldn't you use PF equals M1 V1F plus M2 V0?
Partially use it, but do we know what that is?
No.
No. But what is PF also equal to? You're right, it's equal to this, but what is it also equal to?
PI?
Yeah, and what is PI equal to?
That and M1.
Right, so what is the equation that I write down? Because it's not this one. That's the right-hand side of the equation I want to write down, right?
Okay.
All you have to do, go ahead.
So,
This is true, right?
oh, just, I don't.
Okay, it's all right. This is true though, right?
Yes.
So then, well, this must be true. That's this part. Why? Because it's just equal to PI. Equals, well, then this part, right?
Oh, okay.
Very, very important. And I mean, I could say, oh, it's simple. All you have to do is, oh, PI, plug it in right there. That's all I've done. But it's important that you see that.
Okay. That does make sense, actually.
Good. This is it. So, what would I say? Like, this is what you realize. That's how you do it. And I guess just keep it in your brain and look at it again until you get this process down over and over. It's the same thing. Okay. And then, well, solve for VF. That's 0. Yeah.
Okay, so you just isolate
Yes.
the two.
Yes, exactly. Starting to make sense a little bit.
Yeah, it does.
Yeah. Take your time and be easy on yourself. It's tough. Okay. This is the process, and this is what we're going to do again. And let me tell you what, for inelastic collisions, it's pretty much the same thing.
Okay.
Using your equation here, and then this process, which you did. You basically did this problem. So let me jump over to the other room. We'll take like a couple minutes break here, and then I'll meet you in the other room. Okay.
Okay. Thank you.
Mhm.